Here we're going to take a look at both isotropic and so-called uniaxial minerals. We're going to deal with isotropic first because they're kind of boring. There's not much going on. Let's say we take any mineral that crystallizes in the cubic system, and well, why not? We will draw a cube. So there's a cube. It could be halite. We could have a perfect octahedron of fluorite or a dodecahedron, which I will not attempt to draw, of garnet. But if we have halite or fluorite or garnet, they all belong to the isotropic system. That means that if light is passing through these minerals, it'll go through the mineral with the same velocity regardless of what direction we choose. So you can move it through the corners or move it through the sides. It really doesn't matter. No matter how light is being transmitted through the crystal, it'll always travel with the same velocity. And so that means if it travels with the same velocity in all directions, that no matter how you flip this crystal, turn it around, etc., you will always just have one value for n, the so-called index of refraction. So the index of refraction for these minerals is the only optical property that they have. Now this is in contrast with the next group that we'll look at, the so-called uniaxial minerals. Here we have this diagram from Dexter Perkins' online mineralogy textbook, and he shows the case for minerals that are uniaxial. Now what does that mean? It means that they have a distinct direction where the n value will move either fast or slow in one direction and be faster or slower in another. Well, let's be a little more clear. We will have a direction that we will call omega, which is parallel to the c-axis, and this is called the optic axis, and then perpendicular to omega, so here's omega for this hexagonal fellow here, we will have a direction that we'll refer to as epsilon. And we could do the same thing over here. We would have epsilon over here, and then epsilon over here. And because we have minerals, in this case, that are all in the hexagonal or tetragonal system, these axes here that are perpendicular to C are all the same. We would call this A1 and A2, or over here in the hexagonal system, we would have an A1 and then an A2 over here, and then an A3 that would be front to back. But those are all the same measure, and they're not only the same measure in terms of distance for plotting faces on a crystal or atoms inside of the crystal, they would also be equivalent in terms of how light travels in those directions. So we would have an n epsilon for the velocity of those light waves, or rather the inverse of the velocity for how they travel in the A1, A2, A3 directions, or A1, A2 here, and then the n omega. And then the n omega would be indicative of the velocity as it travels along the c-axis. Keep in mind, although I'm saying velocity n is really the velocity in a vacuum divided by the velocity in the mineral. So all of these n values are inverse velocity. The larger the n, then the slower the velocity. So that's what's going on in uniaxial minerals. We call them uniaxial because they have a single optic axis. And that optic axis is a case that when you look down in this direction, all you see are the A values, and so everything is the same. If you're looking down, if you cut the mineral like this, and so you look at it in cross-section, so for that mineral you would see something like that, for example, then everything you would see would be vibrating in, let's say, the A1 or A2 directions. And since all the light vibrates in the same velocity in both those directions, it is a special case where you're looking down C where the mineral looks isotropic, where everything you see looks like it's traveling in the same velocity. But let's say you were to cut the mineral in some other direction. Let's say you were to take a vertical slice through here. So in this case, now you're looking down this direction here. What I've drawn is epsilon, and we'll just draw that face there. You would see that sort of diamond-shaped face there, and then the crystallographic direction over here would be the omega direction, and then the optic direction would be omega here, and then epsilon coming perpendicular and also in and out of the board. And so this omega would not be equal to, so n omega is not equal to n epsilon. It can be either a faster or a slower direction. We'll look at that later. But this difference, n omega minus n epsilon, is something we refer to as delta. And delta has a special name. We call it birefringence. So we'll look at this in another diagram, but for this YouTube video here, we just want to introduce what's going on with the rays in terms of their relative velocities and their and the paths in which they take through the crystal. In this case, the n omegas are always going to be related to the c-axis, and then the n epsilons will always be related to one of the equivalent a1s, a2s, or a3s. And then if you have light that's moving in some random direction, not parallel to any one of the A's or the omegas, let's say it's moving off at some angle in between, let's say A2 and omega, or the c-axis here, then in that case its velocity would be somewhere in between. So we call this epsilon prime, and epsilon prime would be something intermediate between omega and epsilon. It doesn't have to be the case that omega is the largest. It could be that we have epsilon is greater than epsilon prime is greater than omega. But whatever epsilon prime is, however omega and epsilon are relative to one another, the value for epsilon prime, or the index of refraction along epsilon prime, will be intermediate. So one of these will represent the maximum and minimum velocities, and then any other random direction would be intermediate between those.